Today's module begins with Chapter 4, Atmospheric Moisture. You should really begin to have some curiosity in terms of learning about moisture because of how you use it in forecasting. You have to use it for predictions of clouds, predictions of sufficient moisture that will help support precipitation, and so we'll learn a little bit about it today, specifically these 4 points. We'll look at the role of water in the atmosphere. We'll also look at terms and definitions for atmospheric moisture, the impact of moisture on comfort, and then we'll look at some instruments used to measure moisture. The term here, water vapor, refers to water in the gaseous state. As you'll recall from Chapter 1, water vapor is a variable constituent in the atmosphere. It makes up anywhere from 0 to 4% of atmospheric composition. The term humidity is a word that we use to describe the amount of water vapor in the air. Okay, here's your first puzzle. Where do we have more water vapor? In the Sahara Desert or in New England? Well, it depends upon the type of humidity that we were referring to. Before we get to that, let's take a look at the molecular structure of water in the atmosphere. On the left here, you see H2O, 2 atoms of hydrogen and 1 atom of oxygen that you see right here. There's an angle that separates the 2 hydrogen atoms. Don't worry about that, that's not important, but the thing that you should notice is that at the base of the oxygen atom here, it has a negative charge. The hydrogen has a positive charge, therefore they are attracted to each other. And in the right-hand figure, you get a group of these molecules together, and you can have water in 3 phases, either in a vapor, a solid, or a liquid. Now, if you think about it, remember we talked about molecules gaining energy. Now, if one of these molecules here that, let's say for instance this is the solid form of water, and let's say it gets enough energy, it begins to break away and it moves away from this particular structure. It can go directly from ice to vapor, which we call sublimation, or it can go from vapor directly to ice if it attaches to an ice crystal. So that gives you an idea of the molecular structure of water. This term here, saturation, very, very important. Before we actually get to the terms here, what you're looking at here is a glass filled with water, or actually half full with water. You see here the cursor, this is the top of the water. You see the water molecules, the water in liquid form here. And then you see water molecules here that are in the gaseous form. Now notice the directions of the water molecules. You have some water molecules going from liquid into the vapor stage, that's the gas stage, and you have some of these water molecules that are in the gaseous stage moving down, becoming liquid. And so you've got movement of water molecules from liquid to vapor and from vapor to liquid. When this process here is in equilibrium, in other words, when you have an equal amount of water vapor condensing, turning into liquid, and an equal amount of water vapor molecules going from liquid into the vapor form, this is a term called saturation. Okay? It's the balance between basically evaporation, going from liquid to vapor, or condensation, going from vapor to liquid. Now, when we use the term saturated, again, we recall that it means evaporation and condensation are in equilibrium. This is a critical concept to understand because we're going to be using this in quite a few applications over the next few chapters. There are some factors, if we look at evaporation, factors that influence evaporation. As you know here, wind can influence evaporation. Temperatures also influence evaporation. In other words, warm water enhances evaporation. Recall when we talked about the average molecular speed representing temperature. We define temperature by the average molecular speed. Higher temperatures have higher molecular speeds, and so then you have some of these molecules breaking away from the water surface and becoming vapor, water vapor, which is water in the gas state. So two factors that influence evaporation: wind and temperature. Here's another important term that you'll need for moisture. It's called condensation nuclei. I don't know if you recall, but in the Chapter 1 video module, I mentioned the fact that you need dirty air to help produce precipitation. That's right, I said dirty air, air that's polluted. And the reason you need that, if you look over here on the right-hand side of the page, we see a water vapor molecule that I'm outlining with the cursor. And then you see these pieces, these are called nuclei. These can be ash, they can be smoke from a plant, they can be salt particles, they can be dirt from the road, anything that can be suspended, which we call aerosols, suspended in the atmosphere. In some cases, what will happen, these vapor molecules, these water vapor molecules, will stick to these nuclei. And if you get enough of them sticking and they begin to cool, you can have condensation. Well, recall that with cooling, when we talk about temperatures being cool, that implies a slower molecular speed. And so these vapor molecules, if they're going at a slower molecular speed, can attach to these condensation nuclei. Whereas heated vapor or very hot vapor, moving very quickly, bounces away from condensation nuclei and has trouble actually condensing. You may have heard the term somewhere that basically warm air holds more water than cold air, or holds more moisture than cold air. We'll see exactly the science behind this as we go through the next several slides here. Basically, no matter how cold the air is, it does have some water vapor present. And basically what we can say here is that saturation, recall what saturation is, it's the equilibrium stage between evaporation and condensation. It's more likely to occur in cool air than in warm air. Now you might be thinking, why is that? Well, again, think about it. That previous slide we started talking about condensation nuclei that you see right here. And so the slower these water vapor molecules are moving, the more chance they have to stick to this nuclei. It needs a base to be able to condense. And so therefore we say that saturation is more likely to occur in cool air because you're more likely to have that balance between water vapor condensing into liquid and liquid water evaporating into water vapor. So in other words, we can say that warm air has a higher capacity for water vapor. Remember, water vapor is in the gaseous state, and if you have warm air, you have fast-moving water molecules, water vapor molecules, they can stay in the vapor state. And so therefore it has a higher capacity. In other words, it holds more moisture or more water vapor than cold air. Now we'll illustrate this with a graph here shortly. This particular slide is basically the hydrological cycle, or the hydrologic cycle I should say, and basically it's just a balance of water across the atmosphere, subsurface, the surface, and the oceans. You've probably seen this type of schematic in a lot of your science books when you were in school. Let's start off with the ocean. As the ocean begins to warm, we begin to get some of these liquid water vapor molecules. They gain enough energy, they begin to break away from the surface. So they go from liquid to water vapor, and so you have evaporation occurring. As we begin to lift the water vapor up, it begins to cool. And eventually it will cool to a point to where it will condense into a cloud. And so then you have the cloud being advected or moved from the ocean to the land. And as we'll learn in a later chapter, there are processes that go on within the cloud that help produce precipitation. So we get some precipitation over the land. And if it's cold enough, especially in some of the higher elevations, you'll begin to get snowpack. So you have ice up in the mountains. And in some of the lower elevations, you'll have water running down the mountains. Some of that will seep into the mountains, and basically you'll have groundwater, which will move toward lakes and eventually running off back into the sea. You have evaporation over lakes here. And so you've got this particular cycle from evaporation, condensation, back into the ground, and eventually back into evaporation. Okay, this next slide. This particular picture here that you have is a picture of a air parcel. Now recall from Chapter 1 that our atmosphere is made up of nitrogen, oxygen. In fact, almost 80% of our atmosphere is made up of nitrogen. 20% is made up of oxygen. Actually, nitrogen makes up 79%, oxygen 20%, and then some trace elements such as argon, hydrogen, helium, and some other trace gases. But let's just look at this particular air parcel and think of it as a balloon. In other words, this air parcel, we've got it closed off, and it has water vapor molecules. It has nitrogen, molecular nitrogen, oxygen. And so we have these items available in this air parcel. Now, if you were to look at this air parcel, you would say that it does have moisture present in it, because we just said this is water vapor. Okay, we've got the H2O. And so we have moisture, or we have water vapor in this air parcel along with nitrogen and oxygen. So if I were to ask you to describe the amount of moisture in this air parcel, how would you do it? Well, there are several ways that we can describe the moisture content of this air parcel. We can define it in terms of absolute humidity, specific humidity, mixing ratio, vapor pressure, and a term that you're all familiar with, you've heard it on the nightly weather forecast, relative humidity. And so you see there are many ways that we can describe the moisture content of the air, or in this particular case, one parcel of air that we've pulled out of the atmosphere. Well, let's look at two of those terms on this slide. Absolute humidity and specific humidity, also thought of as mixing ratio. I'll use the term specific humidity and mixing ratio. There is a difference between the two, and we'll see what it is just for a moment. But what I would like to do at this point is to draw your attention to this graphic up here in the top left-hand corner. We have an air parcel here, and as it begins to sink, the air parcel begins to become smaller. In other words, its volume begins to decrease. So you see the air parcel up here has a volume of 2 meters cubed. If we lower it in the atmosphere, it begins to shrink, and in this example, the parcel size is 1 meter cubed. We also know something about the mass of the water vapor in this particular air parcel. It has 10 grams of water vapor. And once it's squeezed down, once the air parcel becomes smaller as it begins to sink, it still has 10 grams of water vapor. We haven't removed or added any water vapor into it. But if we're to define the absolute humidity of this air parcel here, and then the same air parcel but just smaller, it has different humidity. In other words, we look at the mass of water vapor, which is 10 grams in both the larger and the smaller air parcel, and we look at it in terms of mass per unit volume. In other words, the density of that particular air parcel. And so, this air parcel here, if we take 10 grams divided by 2 meters cubed, we get 5 grams per meter cubed. In other words, in this air parcel, the density of water vapor is 5 grams for every meter cubed. of this particular air parcel. If we lower the air parcel, if we bring it down from a higher elevation down to the surface, we see the absolute humidity changes to 10 grams per meter cubed. In other words, the mass divided by the volume. The mass still 10 grams. In other words, the mass of the water vapor has not changed, but the size of the parcel has. And so 10 divided by 1 gives us 10 grams per meter cubed. So in terms of absolute humidity, it doesn't really tell us anything about the water vapor content, but just the density of water vapor content. So not exactly the best measure of moisture in the atmosphere, although it does have applications. But for what we're looking at, probably not the best one to use. Now if we look at specific humidity is concerned with the mass of water vapor and comparing it to the mass of air. We're not saying anything about the size or the volume. All we're doing is talking about the mass of the water vapor and comparing it to the mass of the air. So if we use this example right here, this particular graphic down in the bottom right-hand corner, again we have an air parcel. It has 1 gram of water vapor, and the mass of the air parcel, this entire air parcel, is 1 kilogram. And according to our formula, it's the mass of water vapor divided by the mass of air. And so we get 1 gram divided by 1 kilogram gives us 10 grams per kilogram. Now, if this would have been 10 grams instead of 1 gram, the specific humidity would have been 10 grams per kilogram, because we're comparing the mass of water vapor to the mass of the air parcel. We can also, if we look at it down here, now as we begin to sink the air parcel down, notice that the mass hasn't changed, and the mass of the water vapor and the mass of the parcel hasn't changed. Only the volume has changed. And since specific humidity has nothing to do with volume, then again we come up with the same specific humidity. Mass of water vapor, 1 gram, divided by mass of parcel gives us 1 gram per kilogram. Now the mixing ratio, which is very similar to the specific humidity, is basically the mass of water vapor, how much water vapor in terms of mass you have in that air parcel, divided by the mass of the dry air. Now when we were looking at specific humidity, we had the mass of dry air plus the mass of moist air. With mixing ratio, we're only looking at the mass of dry air. So we're comparing the amount of water vapor to the amount of dry air. In other words, all the other molecules except the water vapor. And so it works the same way as specific humidity. If we look at a mixing ratio chart, this is a chart I pulled off at the University of Wyoming. This is not at the surface. It's at 850 millibars, which is about a mile up in the atmosphere. And typically when we're looking for moisture, we look from the surface on up to about a mile. And if we have sufficient moisture at about a mile up, then we consider the atmosphere moist. But what we're looking at here, and I know this is a little difficult to make out, but this is the eastern coast of the U.S., Florida, again I'm trying to outline with the cursor, Louisiana, Texas, and the Gulf of Mexico is sitting down here. And also notice that we have high values of mixing ratio. Again, recall, mixing ratio is comparing the mass of water vapor to the mass of dry air. So we have very high moisture contents down here in the Gulf of Mexico, just like we would expect. If we look back here over the northeast U.S., over the land areas, we notice the values are 2 grams per kilogram compared to 10 down here in the Gulf of Mexico. So there's much less moisture over the land than there is over the Gulf of Mexico. Now, I think there's a very interesting area up here. If you look, here is Iowa, and most of Iowa is between 1 and 2 grams per kilogram. It's pretty dry at this point. But notice some of this blue beginning to point up or to nose up into northern Missouri and into southern Iowa. In other words, it looks like we've got moisture moving up with this particular chart back on the 18th of January when I downloaded this particular picture. So it looks like we've got moisture, or at least that day we had some higher moisture values moving into Iowa. So if you were doing a forecast and you see this nose of moisture beginning to move up, then you have to consider the possibility of cloud cover and or precipitation. Now, we can look at specific humidity and how it changes with latitude. When we're talking about latitude, we're talking about north to south direction. So we look at the North Pole is up at 90 degrees. Iowa is at about 40 degrees. Part of southern Iowa, we're up in Des Moines and Ames, we're at about 41, 42 degrees north latitude. But you see here specific humidity on the y-axis as we go up is increasing. So we go from 0 grams per kilogram of water vapor all the way up to 18 grams per kilogram. And you notice the highest value of water vapor, about 17 grams per kilogram, is located at about 0 degrees, which corresponds to the equator. And what do you have around the equator? You have a lot of ocean. And so you would expect some of your higher moisture values to be in areas where you have warm, moist, where you have warm oceans. There's a lot of evaporation going on. In other words, the vapor pressure is increasing. So if we look in our area, typically about 40 degrees, on average we have about 7 grams per kilogram. And again, I should remind you what specific humidity is. Specific humidity is the mass of water vapor compared to the mass of air, both dry and moist. So we're taking the ratio, how much of the mass is water vapor compared to the mass of the entire air parcel. And notice as we go toward the poles, the amount of moisture in terms of specific humidity begins to decrease, with the maximum being up here at the equatorial regions. Now, do you notice, if you look at 30 degrees north, the value of specific humidity is about 10. If we look at 30 degrees south, the value of specific humidity is about 9. Now, the interesting thing about this is that most of the world's major deserts are located at 30 degrees north and south. Now, how is it that the Sahara Desert and other deserts located at 30 degrees north and south have higher water vapor content in terms of specific humidity than we do here in Iowa? Remember that puzzle I asked you earlier about, which has more water vapor? The Sahara Desert or New England? Well, we see on average that the Sahara Desert, although it's dry, has quite a bit more water vapor than even what we see here in Iowa. Interesting. We'll learn why the desert regions occur in those areas a little bit later. It has to do with general circulation of the atmosphere. Another way that we can look at moisture, or we can quantitate moisture in the atmosphere, is something called vapor pressure. Now, before we get into vapor pressure, one thing that you should realize, if we were to take a column of air from the surface and move it all the way up into the atmosphere. In fact, let me just go ahead and schematically draw this out. So let's say we have a ground surface here. This depicts the ground. And I were to take, let's say this is the top of the atmosphere. And this is the surface. And I were to take a column of air. And you recall from Chapter 1, most of the molecules in this column of air would be near the surface, and then it begins to thin out as we go up. The reason why we have most of the air molecules near the surface is because of gravity begins to pull those air molecules down. But if I were able to actually take and measure the mass of this column, or you can think of the weight of air in the column. These little red dots are all molecules of air, air parcels. If we were to weigh them, it would come up to be 1,013 millibars on average. Okay, so we're looking at this column of air that we have here going from the top of the atmosphere to the surface, showing a pressure of 1,013 millibars. Recall that pressure is equal to force per unit area. Okay, so each of these air molecules exert a force on the atmosphere. And we can look at this as an area here, as each of these air molecules begin to exhibit a force per unit area. Okay, so the average atmospheric pressure we determine is 1,013 millibars, and part of that atmospheric pressure is made up of vapor molecules. Recall, we talked about nitrogen making up 79% of the composition of an air parcel, oxygen 20%, water vapor makes up anywhere from 0 to 4%, depending upon how much you have in the particular air parcel. And also, recall, we talked about warmer air holding more vapor or more water vapor than cooler air. Recall that warmer air has more energy, the air molecules are moving much more faster, and so they can break away and end up taking the vapor state. And so therefore, we have higher saturated vapor pressures. Now how does that work? That seems a bit confusing. If we say warmer air can hold more vapor than cooler air before it saturates. Do you recall the term saturation? That's the balance between water going from liquid to gas and from gas to liquid. It's that balance where you have an equal number of amount of liquid water molecules evaporating, becoming gas, and an equal amount of water vapor molecules becoming liquid. So we say here that warmer air can hold more vapor than cooler air before it saturates. Therefore has higher saturated vapor pressures. Now this obviously is a bit confusing. This is the first time you've heard it. But this particular graph here, and in fact by the time you view this, you have already done the simulation called Mountain Sim, and you will have become very familiar with this particular graphic. What we have along the x-axis is temperature. We have temperature in degrees Celsius or degrees Fahrenheit. You can look at either of these temperature scales. And then we have something called water vapor pressure. That's the amount of pressure that a water vapor molecule is exhibiting force per unit area. Remember, we define pressure as force per unit area. And you also recall that I drew that column of air, and within that column of air you have nitrogen, oxygen, and you also have water vapor molecules. And so they exert a certain pressure, okay, they exert a certain force over a unit area, and obviously the more pressure the water vapor exerts, that's an indication of more water vapor molecules. More water vapor molecules produce more pressure. Less water vapor molecules produce less vapor pressure. So as we go from 0, which means basically no water vapor in the atmosphere, compared to 90 millibars, which is very high pressure. So that's an indication there's a lot of moisture in the atmosphere. Also notice you have this red line. I'm going to see if I can change the color here just a moment. Let's try blue here. You notice right here that you have a line which we call the saturation vapor pressure curve. Now you recall from Mountain Sim, well actually I'm not going to give that away yet. I'll save that here just a moment. Okay, so the idea here is that higher vapor pressure means higher water vapor content. And so let's just take a look at some values here. For instance, right here at 30 degrees Celsius, if I go up to this saturation vapor pressure curve, and right now you don't really understand so much what saturation vapor pressure means. Actually, I guess you do, because you've been working with Mountain Sim. And so the thing is, I'm doing this video module the day before you're actually working on Mountain Sim. So by the time you've worked on Mountain Sim, you'll see the importance of this saturation vapor pressure curve. Basically, it's where condensation occurs. When you did Mountain Sim and you produced a cloud with rain, it's when the air parcel hit this curve. But for this particular case, at 30 degrees Celsius, an air parcel in terms of water vapor will measure at about 42 millibars. In other words, it exhibits 42 millibars of pressure in the atmosphere at 30 degrees Celsius. And so at 30 degrees Celsius, it is considered saturated if the pressure is at 42 millibars. Now let's take a cooler temperature, 10 degrees Celsius. And 10 degrees can hold a maximum amount of 12 millibars of water vapor. So when we say that warmer air can hold more water vapor, in other words, we determine water vapor content by the amount of pressure it's exerting. Higher pressure, higher water vapor content. So at 30 degrees Celsius, we reach the saturation curve at about 42 millibars. In other words, if you have an air parcel that's 30 degrees Celsius, which is about 86 degrees Fahrenheit, it can hold a maximum of 42 millibars of water vapor. Whereas you go down to 10 degrees Celsius or 50 degrees Fahrenheit, it can only hold 12 millibars. And if you look up here in this particular graph, these are vapor pressures, saturation vapor pressures for ice and liquid. Notice that the pressures for ice typically are smaller at a particular temperature compared to liquid water. Do you know why? Think about the average molecular speed of molecules when it's in the ice stage versus liquid stage. Okay, so we've talked about this saturation vapor pressure curve here that we see. And let me go ahead and set up my pencil here. Now this is the saturation vapor pressure curve. And so in our previous example, if we have an air parcel at 30 degrees Celsius, its saturation vapor pressure curve, in other words, where it intersects the saturation vapor pressure curve, is 42 millibars. But let me ask you this. Let's say, for instance, that at 30 degrees Celsius, we have an air parcel. Let me see if I can adjust this a bit. Let's say that we have an air parcel that at 30 degrees Celsius has a pressure, a vapor pressure. I'm just going right over to the vapor pressure line of about 20 millibars. So the actual vapor pressure of this particular water vapor molecule at 30 degrees is 20 millibars. So we can actually measure the actual vapor pressure, and we say it's 20 millibars. The question is, how much can that air parcel hold, though? How much more vapor pressure can that air parcel hold? Think about it a second. This is the actual vapor pressure if I stop the parcel right here at 30 degrees and go over here and I measure it at 20. At 30 degrees, we know at maximum it can hold a vapor pressure of 42. But I'm telling you the actual vapor pressure in this example, the actual is 20. But it can hold a maximum of 42. Can you think a way of describing that? graphically, if an air parcel at 30 can hold this much water vapor, in other words 42 millibars, but it's only has about 20 or 21 millibars of pressure, then I would say that it holds about half the amount of moisture or half the amount of water vapor that it could at this particular temperature. This is actual and this is theoretical of what it could hold at 30 degrees Celsius. So I would say that if I were to describe this, notice that this is about midway between 0 and about 42. So I would say it's about half full of what it could hold. So if I have a temperature of 30 degrees Celsius, I would say it's holding about half the amount of water vapor that it could actually hold. And so you see right here, we have some definitions. Vapor pressure. It's the air's total vapor content. In other words, I'm saying that the vapor pressure, that's how much that's actually in this air molecule. And then I can describe it in terms of saturation vapor pressure. How much water vapor is necessary to make the air saturated at any given temperature. At this point here, the air is saturated because it's intersecting this saturation vapor pressure curve. You can put it this way. The saturation vapor pressure is the pressure that the water vapor molecules would exert if the air were saturated with water at a given temperature. In this particular case, 30 degrees Celsius. But again, think back to what I said. In this example, this is the actual vapor pressure. This up here is what we call the saturation vapor pressure, what it could hold at 30 degrees by intersecting the saturation vapor pressure curve. Let me give you a formula. Vapor pressure divided by saturation vapor pressure times 100 gives you something we call relative humidity. That's what we mean by relative humidity. We look at how much vapor pressure is present and compare it to what it can hold, the saturation vapor pressure, at a particular temperature. And we multiply by 100 to get a percentage. So again, the vapor pressure, what is actually in this air parcel, compared to what it could hold at this particular temperature, where it intersects the saturation vapor pressure line. So in this particular example, let's say my vapor pressure is 21. Actually, it's about 20. Divided by what it could hold at that temperature, which is about 42. So we've got 20 divided by 42 times 100 gives us approximately somewhere at around 48-49% relative humidity. But notice, and this is the shorthand notation, VP, vapor pressure, divided by saturation vapor pressure times 100. Now notice, since we're dealing with saturation vapor pressure, that is dependent upon temperature. It's temperature dependent. Let's say, for example, let me go ahead and erase this here. Let's say, for instance, we took that air parcel that we had and we cooled it. Let's say we cooled it to 20 degrees Celsius. It still has the same amount of water vapor, right? It's still at about 20. And so vapor pressure is still at 20 millibars. Well, the question I have for you, since it's right here, what is its saturation vapor pressure at 20 degrees Celsius? Well, we would go up until we hit the saturation vapor pressure curve and go over here, and it could hold about 25 millibars worth of moisture at 20 degrees. So this same air parcel, we haven't changed the moisture content because it's still 20 millibars as it was when it was 30, but we've just changed the saturation vapor pressure. In other words, it becomes saturated as we begin to get cooler. So now our relative humidity, vapor pressure, which is 20, over saturated vapor pressure, at our new temperature of 20 is now 25. And so that's 4/5, which is 80%. So now our relative humidity has gone from around 50% to 80%, even though the amount of moisture hasn't changed. Kind of mull that over. I realize I'm throwing a lot at you here, but this should make sense, that relative humidity is temperature dependent, and we see that. We have a graph here of the different times throughout the day versus temperature, and in the evening hours as temperature begins to decrease, assuming we keep the water vapor constant. In other words, we don't change the amount of moisture in the air, but because relative humidity is a function of saturation vapor pressure, which is a function of temperature, that as the temperature decreases, the relative humidity increases. We just saw that with the previous example that we just did. I took this air parcel that had 20 millibars of vapor pressure, I cooled it from 30 to 20, and we saw that the relative humidity went up to 80%, although the amount of moisture has not changed. And so as temperatures begin to increase as we go through the day, relative humidity begins to decrease. And I can show you how that would work. Let's use the same example here. Let's say I take this air parcel at 30 and I warm it to 40. It still has 20 millibars of vapor pressure. That hasn't changed. But the saturation vapor pressure, I go straight up at 40 degrees. Its saturation vapor pressure is now 70. So I take 20 divided by 70 times 100, and that's going to give me a value less than a third. So we're somewhere probably around 26, 27%. I don't have a calculator in front of me, but you can see that the relative humidity has gone down even though the amount of moisture hasn't changed. Well, you're probably wondering, why are we using relative humidity then if it doesn't tell us anything about the amount of moisture in the air? Well, actually, it does give us some indication of how close to saturation we are, right? If we're close to saturation, in other words, that balance between evaporation and condensation, if we're close to saturation, and you learned from Mountain Sim, the closer we are to this curve, the closer we are to saturation, and the closer we are to actually producing condensation or a cloud. So relative humidity is useful. It gives us an idea of how close we are to saturation. Let's work a couple of examples here. Let's take a vapor pressure of 10 millibars and a temperature of 20 degrees Celsius. So let's see, here's 20 and a vapor pressure of 10. Now, this is our actual vapor pressure, which is 10. At 20 degrees, the saturation vapor pressure, if I go straight up from 20, and I intersect the saturation vapor pressure curve, that's about 22. So saturation vapor pressure is 22. So if I take 10 divided by 22 times 100%, that gives me a relative humidity less than 50%, right around 47%. And so we can actually calculate relative humidity from that. Now we'll work another example here. Let's say that we start with a temperature of 30 degrees Celsius, right here, and we hold the water vapor content constant at 10 millibars. So let's go 30, and about right here is 10 millibars. And so my question to you is, how can we achieve a relative humidity of 100%? Okay, we're starting at 30 degrees. And we're not going to increase the moisture. So I can't raise this parcel. I cannot increase the vapor pressure. That's increasing the water vapor. I say we hold the water vapor constant. Can you think of any other way to reach this line? Well, what if we move this air parcel closer to the line? And eventually we reach saturation. What have we done to this air parcel? We've moved it from 30 degrees to about 5 degrees. So in other words, we have cooled this air parcel. So we see that cooling can produce condensation. And that's what I was just showing in the previous example. We can cool to saturation. So in this particular example, if we have an air parcel sitting on the saturation vapor pressure curve, its actual vapor pressure is about 22. So vapor pressure is 22. Since it's on the saturation vapor pressure curve, its saturation vapor pressure is also 22 millibars. And so we take relative humidity. We use our formula, which is vapor pressure divided by saturation vapor pressure. 22 divided by 22 is 1 times 100, gives us a relative humidity of 100%. In other words, this air parcel sitting at 20 degrees, if it has a vapor pressure of 22, that's the maximum it can hold since it's sitting on the saturation vapor pressure curve. This is what we define as dew point temperature. Dew point temperature is when we take an air parcel and we cool it to saturation. In other words, when we cool it, when it condenses, we call that the dew point temperature. So let's take a look at the relationship between relative humidity and dew point temperature by working a couple of more examples here. In this first one, let's say we have a temperature of 10 degrees Celsius and a relative humidity of 100%. Well, to have a relative humidity of 100%, we have to have vapor pressure and saturation vapor pressure being equal. The vapor pressure, the actual amount of water vapor, is about 12 millibars. The value on the saturation vapor pressure line at 10 degrees Celsius is also 12 millibars. So that is a relative humidity of 100%. So if we have a temperature of a parcel at 10 degrees, what is its dew point temperature? Well, its dew point temperature is also 10 degrees at this point. Is this starting to make some sense? If not, I'd encourage you to go back to Mountain Sim and use the controls and see the different dew point temperatures based upon the different simulations that you run from Mountain Sim. Well, some practical applications of the dew point temperature. Well, we know that actually the actual air temperature cannot drop below the dew point temperature, right? Let's say, for instance, we take an air parcel here at 30 and we cool it until it condenses. This point is the dew point temperature. Once we go from water vapor to liquid water, recall that we have a phase change and we release latent heat. We release it and it becomes sensible heat. You recall that, I believe we talked about that in Chapter 2. When we have a change of phase from water vapor to liquid water, we actually liberate the hidden heat, which we call latent heat, into sensible heat. That sensible heat is used to warm the air, so we cannot cool the actual temperature below the dew point. So, if we have conditions with clear skies, light winds, oftentimes the temperature will cool down to near the dew point temperature. As you're going to learn in Chapter 5 module, you can use the dew point to predict the occurrence or non-occurrence of fog, frost, and dew. We can also predict the height of the base of a cumulus cloud by looking at dew point temperatures, although for this particular course we will not be doing that. And we can also look at dew point temperatures as an indication of high and low moisture content. Higher dew points, in other words, if we've got an air parcel here, its vapor pressure is 42, its dew point temperature is 30. Here, the temperature dew point is 20. Its vapor pressure is 22, so it has less moisture. Lower dew point, less moisture. Higher dew point, higher moisture. So you can help to forecast for clouds, precip, those types of applications. So you see there are quite a few practical applications of dew point temperature. We see some of the seasonal dew point maps during January and July. This is dew point maps here in January. And obviously the higher dew points are along the Gulf Coast, as you would expect, and the lower dew point temperatures are up in Canada. During July, again, the higher dew points are down in the southeast, but even up here in Iowa, we have dew points on average between 60 and 65, very high. And the coolest dew points are again up into the Canadian regions. Also notice that Reno, in that area, they have lower dew points in the 40s. Let's do a comparison of relative humidity and specific humidity. You probably remember this particular graphic. Again, we are looking from 60 degrees north to the equator at 0 degrees to 60 degrees south. And we saw that as we went from north to south, okay, going from near Iowa at 40 degrees north latitude to the equator, we see that specific humidity begins to increase. Okay, you can tell there by higher values. However, if we look at this, we see that humidity begins to decrease as we go from the poles to 30 degrees, and then begins to increase as we head toward the equator again. And then as we go into the southern hemisphere and go from the equator to about 30, again the relative humidity decreases, and as we head toward the poles, relative humidity begins to increase. So, relative humidity is an indication of saturation. Reveals that the desert air is far from saturated. But most of the world's major deserts, like I said, are located at 30 degrees. And we can see that the relative humidity at 30 degrees north is a minimum, and the relative humidity at 30 degrees south is also a minimum. And so we can say that while there may be a lot of water vapor in the desert regions, with the extremely high temperatures, it can hold more water vapor, so it's further away from saturation. So that's why we were saying that it depends upon what type of formula that you're using. If you're using specific humidity, then 30 degrees north is showing more moisture compared to 40 degrees. But if we use humidity, the actual values are still the same. However, they're further away from saturation. Sources of moisture, where we bring in some of the warmer dew points, the Pacific air, or actually the Pacific Ocean, actually brings in cool air, but it also brings in some moisture. The Gulf of Mexico is a huge source of moisture for the eastern half of the U.S. And in fact, when you're forecasting for the presence of moisture, you would look at the winds to the south of Iowa, if you're making a forecast for Iowa, and seeing if those winds are advecting or bringing in moisture from the Gulf of Mexico. Let me ask you this. Let's say we had high pressure sitting out off the coast of Florida. We know that winds are clockwise around high pressure. And so if you have high pressure sitting out here, you have winds coming in from the south, bringing this warm, moist air up. What if you have high pressure sitting up over Canada? Well, winds are still clockwise, but notice in Iowa we're bringing in air from Canada. And we know that typically air in Canada doesn't contain as much moisture. So depending upon the orientation of the high pressure will determine whether you're bringing in moisture or not. We'll just take a moment to talk about relative humidity and comfort. If you've ever been down south, you've probably, especially during the summertime, you may find that you perspire quite a bit. And we talked about getting out of a shower in the morning and you have evaporation and your body begins to feel cooling. Well, if you're down in the, especially where I'm from Louisiana, there's not a lot of evaporation that goes on. You may be perspiring, but you're not evaporating much of the perspiration from your body. And so therefore your body cannot cool. And so if the air is unsaturated, it can absorb more water, let's say, from your body, which produces evaporation, which we said is a cooling effect. So in the winter here in Iowa, it's not unusual to get out of your shower in the morning and the evaporation begins to occur and your skin begins to become colder because it is using energy to evaporate some of that water. Heat index. You've probably heard this value here. They talk about heat index warnings, especially where I'm from down in Louisiana. It's a combination of the relative humidity and the actual air temperature. So for instance, let's say we have an air temperature. Well, let me give you an example in Louisiana. It's not uncommon to see relative humidity of 80% in July and August, and air temperature near 100 degrees. You would see here that we're in the very hot region. But in Iowa, we might have 80%, or let's just say 70%, and our temperature only gets up into the upper 80s. Then we're in a condition where it's very warm. So the amount of moisture in the air determines how high. Okay, this particular instrument called the Sling Psychrometer is a way of measuring the amount of moisture in the air. And let me just basically show you exactly how this works. We have a device here that rotates. In this particular case, it can rotate like this or like this, clockwise or counterclockwise. And there are actually two thermometers. There's what we call a dry bulb thermometer, the bulb down here, and what we call a wet bulb. In other words, we have a piece of gauze over the end of the thermometer here. And what we do is we wet this gauze here. And so we have a dry bulb and a wet bulb. And so we sling it around, and I've actually demoed this in class for you. And we will sling the psychrometer around for a while until the temperature stops dropping. It'll drop to a certain point. And then once it drops to that point, we look at something called the depression, or the difference between the dry bulb and the wet bulb. We subtract those. So let's say, for instance, the dry bulb temperature reads 70 and the wet bulb reads 60. That means we have a depression, a difference of 10 degrees Celsius or Fahrenheit. In this particular case, it would be Fahrenheit. And so from that, we can look at a table of what we call depressions or differences, and we can actually figure out the relative humidity. So it's an indication of the amount of moisture. The more evaporation that occurs, the more cooling we'll have on the wet bulb. Okay? So if there's more evaporation, we'll have more cooling, which means the air is drier. If there's hardly any movement at all, in other words, there's very little evaporation going on, there's very little cooling, then that means this particular wet bulb thermometer will not decrease in temperature. We have what we call hair and other types of hygrometers, where you can have exposed human hair, and based upon the amount of moisture in the air, the hair will either lengthen or shorten. And as the hair begins to, let's say for instance, begins to shorten, then what would happen is that this lever here would begin to move up, and so we would see the ink trace going like this, and it begins to lengthen. This would begin to go down, and so it would look something like that. And so we can use what we call hygrometers to measure the amount of moisture in the air. And you see right here it says that human and horsehair becomes roughly 2.5% shorter as relative humidity drops. Okay, so as it would drop, as the relative humidity would drop, the hair begins to get shorter. We see the humidity decreasing. We have some other types of hygrometers in terms of electrical resistance and infrared type instruments. Well, we reached the end of this particular module. I'd recommend that you go through this brief review. This is out of your textbook here, and just make sure you understand the concepts expressed here in this particular module. Have a good day. Okay, this particular instrument, called the Sling Psychrometer, is a way of measuring the amount of moisture in the air. And let me just basically show you exactly how this works. We have a device here that rotates. In this particular case, it can rotate like this, or like this, clockwise or counterclockwise. And there are actually two thermometers. There's what we call a dry bulb thermometer, the bulb down here, and what we call a wet bulb. In other words, we have a piece of gauze over the end of the thermometer here. And what we do is we wet this gauze here, and so we have a dry bulb and a wet bulb. And so we sling it around, and I've actually demoed this in class for you. And we will sling the psychrometer around for a while until the temperature stops dropping. It'll drop to a certain point, and then once it drops to that point, we look at something called the depression, or the difference between the dry bulb and the wet bulb. We subtract those. So let's say, for instance, the dry bulb temperature reads 70 and the wet bulb reads 60. That means we have a depression, a difference of 10 degrees Celsius or Fahrenheit. In this particular case, it would be Fahrenheit. And so from that, we can look at a table of what we call depressions or differences, and we can actually figure out the relative humidity. So it's an indication of the amount of moisture. The more evaporation that occurs, the more cooling we'll have on the wet bulb. Okay? So if there's more evaporation, we'll have more cooling, which means the air is drier. If there's hardly any movement at all, in other words, there's very little evaporation going on, there's very little cooling, then that means this particular wet bulb thermometer will not decrease in temperature. We have what we call hair and other types of hygrometers, where you can have exposed human hair, and based upon the amount of moisture in the hair will either lengthen or shorten. And as the hair begins to, let's say for instance, begins to shorten, then what would happen is that this lever here would begin to move up, and so we would see the ink trace going like this, and it begins to lengthen. This would begin to go down, and so it would look something like that. And so we can use what we call hygrometers to measure the amount of moisture in the air. And you see right here it says that human and horsehair becomes roughly 2.5% shorter as relative humidity drops. Okay, so as it would drop, as the relative humidity would drop, the hair begins to get shorter. We see the humidity decreasing. We have some other types of hygrometers in terms of electrical resistance and infrared type instruments. Well, we reached the end of this particular module. I'd recommend that you go through this brief review. This is out of your textbook here, and just make sure you understand the concepts expressed here in this particular module. Have a good day.